You're on. Yes,
Yeah,
thank you.
muted, yeah.
Thank you. So welcome everyone. My name is Mathias Bo-Stewart. I'm an associate professor here at DTU Compute. So we are here for the PhD defense of Emil. I'll say a bit more about that. First, I would like to welcome the examiners. We have Professor Manuel Roveri from Politecnico di Milano. We have Associate Professor Pinar Støssen from IT University of Copenhagen. And we have Associate Professor Luca Pezzarosa from DTU Compute. I would also like to welcome the supervisors, Professor Xenophon Fafotis and Professor and Head of Department Jan Madsen. Finally, I would like to welcome everyone else in the room. So what is going to happen now is that we have the PhD defense of Emil Njord, who will first give a lecture with the title Data-Aware Embedded Machine Learning, which is also the title of the scientific thesis that Emil has handed in some months ago. There were some copies up there. I think they are all taken by now.
Oh, there might be one up there.
There might be one left if someone is interested. So the PhD research project has been carried out here at DTU's Department for Applied Mathematics and Computer Science, in short DTU Compute, under the supervision of Montas and Jan, as welcomed earlier. After the lecture, which should have a duration of around 45 minutes, we will have a short break. If people do not wish to stay for the questioning part, feel free to leave at that point. And after that, the examiners will first get a chance to ask questions. We'll get back to how that is done when it is time for that. Once the examiners have asked the questions, the space for the supervisors to ask questions. And finally, if there's time remaining and someone in the remaining audience has questions, there will be time, there will be opportunity to ask those. So as mentioned, the time for the lecture is 45 minutes, and in total, this session may last no longer than 3 hours. And with that, I will give the floor to you, Emil, for your presentation.
Thank you very much, Matthias. And of course, a huge thanks to all of you in the room and those of you joining in on Zoom for joining me for this big day. I'll get started right away with presenting the main points of my thesis that, as Matthias said, is called Data-Aware Embedded Machine Learning. And I hope you're going to understand a little bit more about what that is in the next 45 minutes. Oh, this is a great start. We need to click here, then it works. Perfect. So I'll start out with what was perhaps a couple of years ago a bit of a bold claim. That we have these machine learning systems that are really revolutionizing and transforming the world. Now, I'm saying a couple of years ago, this would have been revolutionary or like a bold statement, but I'm sure all of you have, over the last couple of years, grown to interact with more and more of these intelligent systems. Perhaps through a large language model, such as ChatGPT or Google's Gemini model, and you use it as like a digital assistant for everyday tasks. And this is only one small example of what we use machine learning for today. And this proliferation of machine learning into more and more areas of our society really creates a demand for machine learning in everyday devices. Could be, for example, in a factory where you want to use machine learning to detect when your machines are failing in what is also known as predictive maintenance. Another example could be in security camera setups, where you perhaps have a wish to only record footage when you have certain objects in the frame. That way you can potentially reduce storage requirements and maybe save important footage for longer that could help in, say, criminal investigations. Now, The trivial and naive way to create such systems would be to take the embedded systems, that's this little chip you see there, that's often embedded into these everyday systems. You put a radio on that and you communicate with some machine learning model that you put in the cloud. There you have virtually endless resources, so you don't have to care much about how big this model is, how much energy it consumes, and so on. However, this has some consequences going this easy way, because the resources consumed, mostly in terms of energy, becomes magnitudes larger because of high network communication costs and high cost of running machine learning models in the cloud. And this makes this approach, this paradigm, unsustainable in the long run, as this energy consumption will grow and grow the more applications we introduce, and contribute to growing environmental challenges, and also make it prohibitively expensive for smaller organizations or perhaps even developing economies to take part in this machine learning transformation. This is not a challenge that's intrinsic to machine learning, but it's sort of been the way that machine learning has been developed, because we oftentimes prioritized performance over the sustainability of these systems and the accessibility of them. Embedded machine learning, which we're going to talk a lot about today, offers a compelling alternative to that, where we focus on designing lean machine learning systems that can run on low power devices, enabling a new generation of machine learning systems that can be private, energy efficient, and reliable. Now, this all sounds really great. Despite this promise, adoption of embedded machine learning seems to remain rather slow. And I see particularly two reasons or two avenues that we can follow to hopefully increase the speed of this adoption. This is what I call the scalability challenge and the forgotten data optimizations. And we'll get a little bit more into what I mean by that. Start with the scalability part. So, as you can see in this figure, embedded machine learning has by far the most constrained resources compared to, say, cloud-based machine learning and mobile machine learning. But we also have by far the highest number of devices. Furthermore, these devices are deployed in many, many diverse environments around the globe. You could have an embedded system deployed in a city, measuring the air quality. You could have a system deployed on a freight ship, doing predictive maintenance on the ship's engines. Or you could have a device deployed in the jungle, perhaps monitoring the local wildlife there. And as you maybe also noticed, each of these devices look a little different. This is not by accident, because finally, we also have that all of these devices are oftentimes a little different from each other. They are produced by a different company that use different tools. They have different amount of resources available. And this means that these systems are not offering much in terms of interoperability. The ecosystem is very heterogeneous. So creating an embedded machine learning system for one of these devices will not necessarily work with the other devices. So in order to create all these systems, we're going to need a team of engineers that's going to know about machine learning. They're going to know about optimizing machine learning systems, and they're going to have to know about how to develop and deploy embedded applications, something that's very technical, and there's not a lot of people that actually know how to do all three things. We're going to need that for a bunch of different devices, for a bunch of different applications, for up to 15 billion different embedded systems. And this is what I call the scalability challenge. This is simply not possible with the amount of engineers that we have available right now, and it doesn't seem possible to get that amount of people with these skills. So we need to find an easier and more scalable way to create these systems. Moving on to the data part, what I've included here is a stack that sort of outlines the different components you typically see in an embedded machine learning system. Starting from the bottom, we have the hardware, the physical device upon which the rest of the system runs. On top of that, you have the tool chains that support running machine learning on these devices. On top of that, the models, the actual machine learning models. And then when you get to the top of the stack, you have the data that we use to train these models and the data that these models run inference on. And finally, on the very top, you have the applications that we are solving. Now, research tends to focus on the lower parts of this stack, on the hardware, tool chains, and models. It's like this for embedded machine learning. It's also sort of like this for machine learning at a traditional scale. But there has recently been a push in what's called data-centric machine learning towards paying a lot more attention to the optimizations we can actually do to the data that we're using in these applications. And that's exactly what I see could be very useful in taking and adopting to embedded side of machine learning and seeing what performance optimizations we can actually get by working a little bit more with the data that we have available. Just to hammer this point home, I introduced or taken the cover of a few papers that were released in the beginning of my PhD. And if you have good eyes, you can see that they all focus on mostly the lower level of this embedded machine learning stack. So mostly on how can we make models and tool chains, maybe hardware, more efficient. So that's these two challenges, and those are what I sort of built my PhD thesis around, and what I think that, or what my contributions contribute towards solving. So let's get into that with the main content of my thesis. So my thesis consists of actually 3 research papers. First, there is a review paper. We have a paper about a new data set for embedded machine learning. And then we have a new technique for discovering lean embedded machine learning systems that I've come up with that I call data-aware neural architecture search. Let's just get started right away with paper A, a holistic review of the TinyML stack for predictive maintenance. Now, when it says TinyML here, I just want most of you to read embedded machine learning for now. It's basically synonyms. We can get into what small differences there is between this, but I just think embedded machine learning is easier for you folks to understand. This is like the technical term that everyone uses in research. This is not the first review that anyone has written on embedded machine learning. In fact, there's a whole bunch of them, as you can see in this table out here. But what the reason I anyway thought that it was a good idea to write a review like this was that many of these reviews do exactly what we just talked about. They only focus on the lower parts of the embedded machine learning stack. So again, they focus on the hardware tools and the models, and don't really pay attention to what data sets we have available for these sort of systems and what we can do to optimize the way that we work with our data. So this figure you saw before is actually also from this paper introducing this stack that we are then taking a holistic view of throughout the paper. We don't have time today to go through every part of the stack. Then Matthias is at least going to get a little bit angry with me. So we'll just focus on two, namely the hardware and the data. And for the hardware, I'd like to take you on like a journey of someone designing an embedded machine learning system and sort of choices that you're going to have to make, because this sort of forms the constraints that you have to work within for the rest of the stack. One of the most important choices that you have is the type of processor that your system will have. This can be anything from a regular CPU, like you see in your laptops, that can do any sort of task, but not necessarily very efficiently. All the way to some much more efficient processors that are maybe not so flexible, but can do these computations a lot faster, like application-specific integrated circuits, digital signal processors, or graphics processing units. Another choice you're going to have to make is how much memory you'll have. Typically, embedded systems will have two types of memory. You'll have some RAM memory for storing all the data that you're working with on an ongoing basis. And you'll have some flash memory where you store all your persistent memory that you're going to have to use at some point. You're going to have to make also a choice about what sensors you want to include on your system. Do you need to be able to record audio? Do you need to be able to take pictures? Do you need to be able to detect movement in this application that you're designing? You're going to need a sensor for all of those things that you're going to do. And finally, something that is perhaps a little unique to embedded systems, we actually have a choice of the power source. We have other options than just plugging the embedded device straight into the main power, because they consume so little power that it's actually possible to, for example, take a battery and then put the device virtually everywhere, anywhere, and it can run on this battery for a very, very long time. The downside is, of course, that at some point you're going to have to do maintenance on this device to go and replace the battery. Alternatively, you can try out techniques such as deploying the system alongside some energy harvesting system, like a solar panel that harvests energy from the sun and powers the device through that. If you go for something like this, you're going to have to be a little bit more careful with how you design your system, especially if you live in Denmark, as you might have prolonged periods where you don't have any energy, and you're going to have to find a way to deal with that. So all these choices that you make here sort of set the constraints for the rest of your system. And almost whatever choices you make, you're going to end up with being limited in one of these four resources areas. You're going to have a limited amount of memory in terms of RAM and flash, probably going to have a limited amount of computational power, and you're probably going to have a limited amount of energy to do what you want. Okay. And that's what I'm going to tell you in terms of the hardware today. Then moving in to the data part of the review. And I think what's important to first establish here is that embedded machine learning requires specialized data sets. And this might be a bit surprising to some, because if you've done anything related to machine learning, data science, you're going to know that the internet is full of data sets that you can just go straight ahead and download and start using within seconds. However, most of these data sets target an application that is quite complex, like classifying an image into one of 1,000 classes. And these applications just quickly become too complex for the resource constraints that we actually have in these embedded systems. So then you can end up in a situation like this that you've probably all experienced before, where you simply cannot fit what you want into the resources that you have available. With that established, let's have a quick look at the data sets we then have available for embedded machine learning. These are some of them. They're all a part of this MLPerf Tiny benchmark, which is this benchmark that's been established for comparing embedded machine learning systems. If we take those data sets and we compare that to a traditional scale state-of-the-art data sets, then you can see that there are orders of magnitudes smaller. And this can really become a problem when we want to create high-performance systems, even on embedded devices and on the edge. Now, size is, of course, not the only way that you can judge a data set. There are many others. One that we'll focus particularly much on today is the amount of label errors that there are in a data set. And let me give you an example of that. We saw this image of a boy earlier walking along the beach. Whenever some human was originally creating this data set, he probably correctly gave this image the label boy because that's a boy in this image. However, for another image, this person might have made a mistake. He might have seen this knife and decided that looks like a sword to me in this very moment, and introduced a label error. So basically data that is labeled wrong. And this is something that exists in all data sets, at least any data set that's bigger than a few hundred samples, but it's still something that we really want to avoid for two reasons. First, when we are training our machine learning models, label errors basically teach the model to do the wrong thing. You end up with a worse model, and no one likes that. But perhaps even worse, at the evaluation stage, having wrong label errors actually can give you a false result about how well the model works. So you could have a model that seems to work better because it's actually making the same mistakes that you made during the labeling, or even worse, we may not actually be able to detect when a machine learning model is doing well. And I'll just like to strike this point home, because if you have a data set that has a label error rate of around 8%, then basically any machine learning system that you create and test using that data set, if it works better than a 92% accuracy, then it's making the same errors that whoever created the data set did. So you're not able to find systems that perform better than 92%. In reality, when we have really, really large data sets, we don't really know where these label errors are. If we did, we'd probably hurry up and try to get them fixed. But we can have an idea of it still, because we can have an idea of the quality, general quality of labels. So perhaps we know that a small part of the data set is labeled by experts. A little bit larger part of the data set is still labeled by humans, maybe not experts. And maybe the rest of the data set is labeled by machines. And then you have this trade-off between data set quality and quantity, because you create a very small data set of high quality, only using the labels that you know to be almost all correct. You strike some sort of balance between quality and quantity by including some of the little bit less quality labels, or you include all the data that you have. You get a really, really large data set, but you're maybe not so sure about all of the labels. We'll get back to that in some of the other papers, but I'll end it here for paper A. And then at the end of each paper, I'd like to take little look backwards and look at how these papers and contribute to the scalability aspect and the data-centric aspects that we talked about in the beginning. So for paper A, for the scalability part, I've here reviewed the groundwork for industrial embedded machine learning applications, hopefully making it easier for new engineers that are coming into the field to quickly get up to speed on what is what, and they'll quickly be able to go out there and create more of these embedded machine learning systems. On the data-centric side, I have been part of creating the first review on embedded machine learning that actually reviews these data sets that are used in the field. With that, let's move on to the second paper of my thesis, which is called Wake Vision, a tailored dataset and benchmark suite for TinyML computer vision applications. Now, the goal of this paper was to create a new large and high quality dataset to be used in embedded machine learning, which we just saw that we were missing quite a lot. Question, of course, becomes, how do you actually go about doing that? The naive approach would perhaps be to go out and try to gather all of this data on our own. Say we are creating a data set full of images, I could go out and take pictures with my smartphone. But if I want to reach 9 million images, which is sort of the scale that some of these traditional scale machine learning data sets are in, then I, for 3 years, like the length of my PhD, be having to take 6 images a minute, assuming that I worked 24/7. We're already talking about scalability. This is, of course, not at all scalable. So what we do instead is that we bootstrap an embedded machine learning dataset based on one of these datasets that we already have available at a traditional scale. More specifically, we use this Open Images dataset. It's a dataset created by Google, has tons of pictures with a lot of different labels. They basically went to Flickr, if you know that web page, and just downloaded every image there that had a permissive license. But we take those labels that they assign to those images, and we try to condense that into a person detection dataset through some extensive filtering and relabeling. A person detection dataset is extremely simple. It has 2 labels. Is there a person in the image or not? It's really not harder than that. And that also points toward what simple applications we actually sometimes need to solve with these embedded systems. By doing that, we end up creating a dataset that's around 100 times larger than traditional or the previous state-of-the-art datasets like visual wake words, which is heavily used for person detection, and some lesser used datasets like CIFAR 100 and this Pascal VOC 2012 dataset that could also be used for person detection. Furthermore, we also put a lot of effort into reducing our label error rate. I just told you why that's super important. We are basically going from being able to create embedded machine learning systems that perform at a 92% accuracy up to close to 98%, which I think is a pretty big deal. That's going to empower a bunch of researchers to come up with really, really intelligent optimizations that bring us to that 98% mark. Now, we of course can't claim that we are introducing a new state-of-the-art data set for a specific application without comparing ourselves to the previous state-of-the-art data set for this application. So we set up this experiment where we train a mobile net model version 2 with a 0.25 alpha parameter that has something to do with the size of the model. And then we train that on the visual wake words dataset and our Wake Vision dataset. Don't worry too much currently about these two different configurations of the Wake Vision dataset. This has to do with this trade-off between quality and quantity that I introduced to you earlier. What's important is that, as you can see, both on the visual wake words and the Wake Vision test set, which you see sort of in the rows, both of our Wake Vision datasets actually end up training better models than the models trained on visual wake words. So our dataset is not just a domain shift, it's not just different types of person images, it's actually a real improvement over the previous state of the art. And these models were trained for just as long, even though that our dataset is much, much larger. So it's not a question of just training for longer. With this dataset established, we try to take things a little bit further and see if we can figure out some domain insights, something interesting based on this dataset. And one of the things that we do, perhaps try to get this out of the way, is that we run some quality versus quantity experiments. So again, some experiments on like what matters most, high quality data or a lot of data. We do this across two different scales of models. One that's really small, consisting of around 80,000 parameters, and one consisting of 11 million parameters. Then we train these models using datasets of different error rates, one 7%, one 15%, and one 30%. And we train these across different percentages of the dataset being used. And we find something really, really interesting here, which for starters is that for the big model, using the full 15% error rate dataset actually performs better and achieves higher accuracy than using a smaller part, like around 30% of the 7% error rate dataset, which is something that we do not see at all when we're looking at the small model. Furthermore, we also see that the accuracy difference between using the full 7% error rate dataset on the small model is significantly wider than the accuracy difference between the 7 and 15% error rate dataset in the large model. So all of this sort of points toward that quality is more important for tiny models, and that quantity, i.e. the scale of a dataset, is more important for larger models, which is also sort of in line with what the rest of the literature finds. This is also something we can discuss a little bit later. Finally, we do something else that not a lot of datasets do. We introduce what we call a fine-grained benchmark suite, which is additional test sets for our dataset that allow embedded machine learning system developers to test their systems across different fairness dimensions and their system's robustness to challenging scenarios. So for example, using these, an embedded machine learning engineer could make sure that his systems work just as well across different perceived genders and different perceived age groups, so that we're not discriminating anyone. And they can make sure that their systems work well, even when people are far away, when they're in dark or bright lighting conditions, or when you have challenging situations, like you have a depiction of a person, such as a scarecrow, in the image. With that, I'll wrap paper B up. Here on the scalability side, I've contributed with a scalable approach to generating large and high quality embedded machine learning models through bootstrapping these datasets, of course, through bootstrapping them on already established datasets. And on the data-centric side, I've contributed with this new large high-quality dataset for person detection, this quintessential vision use case for embedded machine learning. That brings us on to paper C, called Fast Data Aware Neural Architecture Search via SuperNet Accelerated Evaluation. To get us started here, I think I need to shortly introduce the idea of a neural architecture search to you. Because I'm not, of course, not the first one to recognize that creating machine learning models can be hard, it can take a long time, and it can be really expensive. Therefore, to speed up this process, researchers have proposed what's called a neural architecture search, which is a computer, basically setting a computer to search for neural network architectures. That's a popular type of machine learning models for optimizing some metric, typically accuracy. So then this computer program runs through a bunch of different architectures, figures out which one works best, and then gives that back to the engineer. For embedded machine learning, this is sort of extended to what we call a hardware-aware neural architecture search that extends the idea of a neural architecture search to also include resource constraints. So now we care not just about optimizing accuracy, we also care about how much memory does our system consume. When we have these multiple metrics, it can become a little bit challenging to decide which system is best. Say you have two systems, one that consume a lot of resources, it's very accurate, and you have a system that doesn't consume a lot of resources, but it's not very accurate. Which of these systems are best? It clearly depends on the situation that you intend to use this system in. So you can't really say that one model is better than the other. Therefore, what we output is actually a collection of models that are all better than each other in some way. We also say that they are Pareto optimal or that they are on the Pareto frontier. Now, I have taken this idea and extended it in a way where we also try to look at the data that's being put into these models and the way that we configure this data. If you consider images, then you could think that you can reduce the resolution of an image, you can change the way it's encoded, maybe you can work with a grayscale image instead of an image in color, and all of that can increase or decrease the amount of resources that you use. We can then put that through the same mill as a hardware-aware neural architecture search, and out we'll then get a combination of a way to configure our data and a neural network model that works well together with this way to configure our data. The question then becomes, how does this compare to an equivalent neural architecture search that's just purely focusing on the architecture? And there's a couple of ways that we can look at this. We could say, if we have some certain performance that we want to reach, like 90% accuracy, then can we do so, or can we find systems that reach that at lower resource consumption? This is what we show here. We have the systems discovered by a data-aware neural architecture search on the left, and the systems discovered by a traditional neural architecture search that purely focuses on the architecture on the right. What you can see on the y-axis is that both searches actually manage to find systems that perform at an F1 score of 1. This is basically a perfect model. It's labeling everything correctly. But the data-aware search finds models or systems that can do so at orders of magnitude less resource consumption than the traditional search. We can also try to flip that question around. Say, now I have some certain resource constraints. Say you have a specific embedded system that you need to deploy your model on. Can I actually get higher accuracy within these resource constraints by using this data-aware neural architecture search? And this is what we're showing here. Again, the data-aware on the left and the traditional on the right. And you can see accuracy on the y-axis and see how we are actually finding systems using the data-aware neural architecture search that perform at a higher accuracy within these resource constraints than the traditional search on the right. Now, you might say that this is maybe not surprising, that the data-aware neural architecture search discovers better systems, because we're basically taking one search space, expanding that, being able to find many more combinations of data and models. So of course, there are some better configurations inside this huge search space. But when you increase the search space, it can also take a lot longer to explore this. So our initial hypothesis was actually that maybe our data-aware neural architecture search would in the end find better models, but if you only had a very, very short amount of time to search for these models, perhaps it would be better to have used a purely architecture-focused approach. That turns out, at least in our experiments, not to be the case. No matter how many models we explore, the data-aware neural architecture search actually manages to find better models, which is a bit surprising, but interesting nonetheless. Then finally, we did an experiment where we took our data-aware neural architecture search and we tried to see, what if we change the resource constraints? Are we still able to find high-performance systems using this search? The large one over here, you've already seen that. That was in the second slide about these results. But then we introduced some more resource-constrained devices here. And as you can see, in both of these resource constraints, we end up finding some high-quality systems, and basically, the higher your amount of resources, the better systems we also find. A point I'd like to stress here is that we're actually not sure that, or it would not be certain that if you just took a traditional, purely architecture-focused neural architecture search and applied it here, that we would be able to find systems that would fit inside these resource constraints, as just the resources consumed by capturing the data and storing that and plugging it into the model could easily exceed the resource constraints of these devices. So apart from finding what seems like better embedded machine learning systems using this search, we also enable people to use this system without actually having much knowledge of how many resources is my data actually consuming. So to wrap up on paper C, on the scalability side, I introduced this data-aware neural architecture search that significantly lowers the barrier of entry to embedded machine learning. And on the data-centric side, I've introduced this data-aware neural architecture search that unlocks this hidden potential of adapting data granularities or the way you configure your data to the specific needs of an application, and thereby increasing performance. With that, it's about time to wrap up, I think. Having a quick look again at the contributions in this thesis on the scalability and the data-centric side. So starting with scalability, I reviewed the groundwork for industrial embedded machine learning applications. I helped out with a scalable approach to generating large and high-quality data sets for embedded machine learning. And I created this data-aware neural architecture search that significantly lowers the barrier of entry to embedded machine learning. On the data-centric side, I created the first review on embedded machine learning that actually reviews the data and the data sets that we use in the field. Then I created a new large-scale and high-quality data set for person detection, which is the quintessential vision use case for embedded machine learning. And finally, as we just said, I created this data-aware neural architecture search that creates improved embedded machine learning systems through adapting the data configurations. With that, I'll sort of start wrapping up, but also giving some acknowledgements to folks that have really helped me out these past 3 years. Specifically, I'd like to start with this guy, my supervisor, that's also sitting right here. Thank you very much for supporting me through all these 3 years. It's really hard to imagine that I'm your first PhD student, because I already think that you've been performing an almost perfect job straight from the beginning. I've always been comfortable coming to you, no matter the problem, scientific or not. We could sit down, discuss it in a constructive way, and you were also always, what's happening here? Helpful and constructive. So thanks a bunch for that. Also like to thank my co-supervisor, Jan Madsen, who's also sitting right here. Jan, as was mentioned, you were promoted to the head of our department, unfortunately, quite early on in my PhD studies. After that, we definitely talked a little bit less, but you're still a great help, especially in the beginning of my PhD studies on really getting me started on the right track when I was a bit unsure about like what directions I could really take in this project. So thanks a bunch for that. Then I'd like to thank some of my closest collaborators doing this PhD studies. That's Colby Banbury. I think he's listening in online. Hey there. And Amin Hassanpur sitting right there. Working together with you have really been a blessing. And I really believe that the research that we have done has benefited from us being able to discuss and do some intellectual ping pong of ideas. And I really look forward to being able to continue this in the future and keep doing research with you. Then a huge thanks also goes out to all my colleagues from the Embedded Systems Engineering section and the Tech for Civ section at DTU Compute. Without all of you, these last 3 years would have been incredibly dull. So thank you for all the lunches and laughs that we've had together. It's really made a difference. I'd also like to extend a thanks to VJ and the Harvard Edge Computing Lab for hosting me for my external research day. It's really an incredible opportunity for me to be able to join such a renowned lab that played an instrumental part in really launching this field of embedded machine learning. You really taught me a lot, especially about the importance of involving the rest of our community in the work that we do to really make sure that the work that we do ends up making a real impact. Lastly, a huge thanks goes out to Gabby, my incredible partner in life, who's always with me when things are looking up, but perhaps more importantly, when things are looking down. By doing that, you're sort of a stable rock that I can always rely on and return to, and I really appreciate that. Apart from that, I also really appreciate being able to spend my free time with you, doing all sorts of fun adventures, which gives me a much needed break from some of the very technical contents that are involved in doing a PhD. Could of course be continuing this for a very long time, thanking about all of you here and online, friends and family that have all helped out in some way or another. But Matthias, it's about time, is it not? Yeah. So I'll leave it there, and that's it for my presentation.
Thank you for that. On my clock, it's 48, and considering I spent the first 3 minutes, I think you achieved a high accuracy on the 45-minute target. So now we will have a 5-minute break for those who need it, and then we will have questions afterwards. So it's actually
Something about questions that people have to come and.
Yes, if there are questions from people in the audience, please come and tell me here in the break.
And how would the Zoom people be able to ask questions?
Yes, and on Zoom, write in the chat if you would like to ask a question.
Okay.
All right, I can use the hero and I think it's all this mold and dirt that it got out. Maybe we should run it just with water now to get it out. Yeah, seems like it just. Good. I don't get it. I don't know.
On, in order to talk.
Yeah, it is now
Then
on.
Yeah, but I control it.
So you can shut us.
Good. Okay, welcome back. So now is the questioning part of the discussion part of the defense, where we will open with questions from the committee, and the committee has agreed to do rounds of questions, opening with general questions from each committee member, and then going through the papers in turn, and finally doing a wrap-up. And of course, there will be space for interactive scientific discussion between the committee members and Emil. And starting with questions, we go by the principle of furthest distance traveled. And as Milano is further away than both ITU and Building 322.
Slightly more. Slightly more.
Slightly
But
more.
maybe Luca lives further.
Then please go ahead.
Okay, a couple of big thank you. Thank you for inviting me and for the warm welcome. It is a great pleasure for me to be here, and thank you for the presentation. So I have the privilege to be the first in line asking.
Yeah.
The first one is quite general, such that you can break the ice, and then we will have time to enter into detail. I do like the title of the thesis, where the focus is on data. Let me ask a provocative question. By definition, machine learning is data-driven, so is data aware. So which is your perspective about the thesis, and which are the main differences as a fil rouge among the three works that you presented? So which are the key aspects about the data aware in terms of the survey, the data sets, and then the neural architecture search?
Yeah. I mean, of course, you're right that like machine learning always centers around data, that without data, there's no machine learning. But I still think that like it's commonly known that I think around 90% of the time that people spend on developing machine learning models or machine learning systems is actually spent on like messing with the data, getting it in the right format, finding the right features, and so on. My problem, I suppose, is that I don't think that's quite given justice in like how much research time we put into the data. We oftentimes just as researchers take a data set online, ready to go, and then we spend all of our time improving the model, seeing like how we can train the model faster rather than trying to figure out, can we maybe reduce the amount of samples in the data set that we need to use for training and so on. And I think for my thesis, I'm primarily looking at it two ways, that where I think I'm doing work on data that others is not, is particular in the terms of data sets. You saw previously like that we had some data sets for embedded machine learning that were dedicated data sets for our applications, but they were like really, really small and not high quality compared to some of the other some data sets that we have in larger scale machine learning. And then this idea of data granularity that, and I think this actually, this is maybe quite interesting, because in traditional scale machine learning, you're kind of used to like, if you have some data and like you have large high resolution images, then let's use high resolution images. They contain like all the information that you want, maybe more. So if all you care about is, I want to have a high performance systems, I want to be really good at detecting something, then you use all the data that you have available, and you don't really care about the resources that it consumes. But when you get to embedded systems level, then you sort of enter into a paradigm where the resources that is consumed by your data actually matters for your overall system. And you can perhaps reduce the amount of resources you spend on your data and use some of those resources to create a larger model that's going to perform better, and in that way work with data in a way that you previously just didn't do because you could just use all the data that you have available and don't care about the resources. I hope that answers your question.
Just if you could highlight a few more words about the fil rouge among the three different contributions. So the line connecting the three different contributions, so paper 1, 2, and 3.
I mean, I suppose it's let's see. It's what I've tried to highlight here, that like the papers are linked in this way, that they are all supposed to contribute towards the idea that embedded machine learning, the way it's done right now, is not very scalable, and we need to improve that. That can be done through the review of like getting people into the field. It can be done through generating high quality and large data sets really fast, like what we did for the weight vision data set. You could take another type of data set and do a similar thing, and also create a new data set for embedded machine learning. And the data-aware neural architecture search also like makes it easier for non-professionals to really quickly start creating these sort of systems. And then on the data side, like we also went through that like, yeah, that's another example of how I'm working with data in ways that I would say people didn't do before. That like all the reviews we had on embedded machine learning, they look exclusively at models, hardware, and maybe the tool chains that we use. But I actually do a deep dive into the data we have available, both for embedded machine learning and for predictive maintenance, and describe how they can be used. Then of course I contribute with this data set and the way that we like working with data and data-aware neural architecture search to really push performance.
Okay. Yeah, back later on with technical questions.
Yeah.
So maybe following on that thread of like focus on data, it is common for researchers, or pretty much maybe in industry as well, when we talk about data, we have this picture of a disk, which is also what you had on the slides. But at the same time, in this field, especially when you talk about data at runtime, it's rarely on an actual disk. So is there like any research work on focus on how to optimize that data path from maybe the flash that you often find in these embedded devices to main memory and vice versa?
I'd say when so I think you're touching on something important here. I'd maybe like to like distinguish between the training time and the inference time of these embedded machine learning systems. We didn't get much into this, but oftentimes at training time, when we are creating these machine learning models, training them on some data to be able to work even in embedded systems, that's typically not done directly on the embedded system itself. That is done instead on a larger computer like my laptop or even a cloud server. And there, I guess, like you have the conventional approach of like a big disk that you're streaming data to. And there are quite mature tools that work, that help you to optimize the way that you sort of stream data quickly from your disk and into the model. It's actually something I got to work a lot with as a part of this weight vision data set, because once you get to data sets that are like having 9 million samples, then it becomes really, really hard to you can't just take this the whole data set, put it in memory, and then feed it one by one. You sort of have to stream it slowly from disk into memory and then to the application. I think the main point is that you're going to have to like somehow parallelize the sort of loading of data and the feeding of data to the machine learning model and to the accelerator, GPU, or whatever is training the model, so that it's not when the accelerator or the processor needs the data that you start loading it from disk. You should have like a sort of look ahead for the next 10 samples that needs to be fed to this model. Now, when we get to the inference side, like once we've deployed the model to an embedded system, then I'd say it's much less mature, the work that is done on that, and you're probably going to have to do some of this work on your own when you are when you're designing the embedded system, and maybe that is some future research that some people could do to like create a better framework for like loading data in a scalable manner. I will say that I'm not sure you're correct in that when you deploy one of these machine learning systems to an embedded system that you're going to be streaming a lot of data from Flash. I think actually what's happening instead is that like you have these sensors on your embedded devices, and you're going to be working with the data as it's coming in from the sensor, and what you really need to do is to optimize the moving of memory from whatever buffer this sensor has into whatever area of memory that the processor or accelerator that you're using should work with. Yeah.
What happens after? Maybe just a quick follow-up.
Yeah.
I agree with you that most of the time you get it from the sensor and then do the operation in memory, but what happens then to the output?
So what happens to the output? Like just a question of like what happens now to the output? Or, yeah. I mean, of course, it depends still on the processor that you use and the framework that you use for running these models. Typically, in the most commonly used libraries at the moment, I believe it's as you reserve some sort of area in your memory that is then reserved as the output of the machine learning model. And then of course, you're going to have to write some application logic afterwards to be able to handle that output and to make the application do what it's supposed to with that information. Yeah.
Yes, okay. So I was open with a very general question. Is it going? So you present these three works, and you've done quite a good job here in the presentation to try to have a common thread, is scalability and data-centric contribution. But they do in the thesis feel a bit of three disjointed work. You started with a survey that is mainly focused on predictive maintenance, then this is completely forgotten. In the other paper, you move into quality of data sets, the contribution on quality of data set, and this is then partially forgotten. It's a bit used in the last one, but then the last one is about narrow architecture search. And I'd like to know maybe a little bit what has been the journey to this.
The journey?
Yes, and what was maybe the initial research question. So how did you move towards, and what was the trigger for the change? These very clean changes and like the stop of predictive maintenance into then working with images and quality of data sets.
Yeah. So, yeah, I mean, you're touching on an important point. Like, of course, research is like many times not this straight road that it is presented to here. So yeah, initially in my PhD thesis, like I expected to have a bigger focus on predictive maintenance for sure. That was sort of part of like the prompt that I got for this PhD studies. I suppose what happened was that we sort of got started. We investigated how predictive maintenance is used with embedded machine learning, and then we wrote this review paper where we tried to take a view at embedded machine learning from a predictive maintenance side. And I don't know, maybe at this point I was a little underwhelmed in some ways, even of like what changes it actually meant to like how little things that would be specific to predictive maintenance in this field. There's a little bit about the models that you work with, like typically for predictive maintenance, you have unlabeled data, so you use some other models than you would do for like image classification, which would mean that the structure of the model would be different, and some optimizations that you run to make these models lean would work a little bit different with predictive maintenance. Then actually the journey worked a little bit different than it's displayed here. Then like I started working a little bit on this data-aware neural architecture search, actually also in the beginning for some predictive maintenance application. But I guess it then showed, and then I later expanded this data-aware neural architecture search to also work on this person detection use case, again showing that like, I came up with one system. It could be used for predictive maintenance. It can also be used for another use case. I guess the maybe least interesting one about like choices that I made is the weight vision data set. I guess that's more about that like this was some work I did when I was going to my external research day, and then like you discuss ideas with the other researchers and try to find overlap in like something that you find interesting. And at that point, I had already been looking a little bit into this idea of data-aware neural architecture search, trying to push some data-centric ideas into embedded machine learning. And there they were having a plan to create some new data sets for embedded machine learning. They really wanted to start with this person detection data set, since that's just a use case that seems to be seeing the most attention in the field. So it sort of makes sense, or made sense to us to start there instead of starting with a data set for predictive maintenance or something similar to that.
Okay, because then we're gonna come back later when we talk about paper A on data, but it was like the lack of data and data availability and the extreme variation between data types and sources for predictive maintenance that kind of made you let it a little bit aside.
Yeah,
You mentioned that there is not much data, and
there's not much data, yeah.
Many different systems, and there is this turbofan engines data set. That's the main thing, and
that's true. That's
more than that. So is this could that be a reason of doing?
Yeah, I mean, I suppose you're right in a way that, like, say there were a bunch of predictive maintenance data sets that I could use, then maybe I didn't need to like switch to like trying other applications for my systems. I could like be trying my systems out on a lot of different predictive maintenance data sets to like get new results. That is, yeah, could be part of the reason. I mean, yeah, that's a lot of choices that I made. Like I'm sure in a different dimension, in a different world, I could also have continued looking a little bit more into predictive maintenance and like using different models with it. I know right now there's sort of a push towards using transformer models, which we also know from like these large language models in predictive maintenance, even for embedded systems, because sort of good at keeping attention over what happens over a long time period. I don't know how mature that was when I was starting my PhD, or but yeah, could have been another direction, I suppose.
Yeah, just to clarify a little bit what has been the reasoning behind that this continues, like the unconnected.
I think it's sort of that
partially unconnected.
Yeah,
between the paper. The contribution is there. This is just mainly to understand.
I think if you're looking for a specific point, I'm not sure I can tell you there is one, but then the point is going on the external research day, working on another application, and then once I came back, I'd really like to take some of the other work that I'm working with and actually apply it to that contribution. Yeah.
Yeah, following Lucas' question, I had the same feeling while reading the thesis. And so I tried to understand the perspective of data flowing through the three contributions. And what I wanted to ask you in order to deepen this point is, could you quantify the effort in terms of percentage among the three papers? And if you could say a few more words about the effort in working on datasets, which is on one hand, it is important, but it's typically very time-consuming activities.
Yeah.
Which is your perspective about that?
That's a good point. I think when you're asking about the resources spent on it, then maybe that's going to be a bit surprising enough what you're looking for. But I think the time spent on each contribution has been relatively like the same amount of time, with the asterisks, I suppose, that the review paper was written very early in my PhD, so it was sort of like done at a time where I didn't know so much about the field of embedded machine learning. So yeah, I suppose you would generally say that PhD students are more productive towards the end of their PhD. They produce more work in a single day. So perhaps you could say less work has been going into the review paper. That was also like done in two iterations. The data set, it's also a little bit hard to quantify, because the data set paper was like, in reality, we've probably been working on it for 2 years now, with like an intensive period of 6 months when I went on my external research stay. But then there has been like some time before the external research stay where I was getting into the idea, like what things do we actually want to achieve with the data set, then really working a lot on it. And now like we've mainly been doing small fine tuning to the data set, maybe fixing errors if someone reported that. Also, we held a competition at this Edge ML Summit that was last month or so on the data set. We also have some new learnings from that I'm probably still going to be working on towards even when I'm done with this PhD. So, I mean, perhaps that is in the long run taking a longer time, because it's taking focus over such a long time. But the intensive work of like putting together the data set, like downloading the open images data set and figuring out how to change that to achieve what we want here, it was probably also around a year, just like and then so again for the data aware neural architecture search. Perhaps you can tell me if maybe I'm getting too much out of the question with answering that, but I think maybe with the data aware neural architecture search, I did pay a little too much attention for a long time on like making sure that the code was really clean, easily readable, picking out what data types are flowing around in the system. And I think if I would change a little bit something about my approach to that, I'd probably be more like, screw it, this is a one-time experiment that I'm setting up and running, and maybe I don't need like super high quality software engineering for that, for those experiments that I'm running there. Yeah.
I think my next question is on first chapter, so I will. Do you have more?
Maybe we can move on
Yeah.
the technical.
Okay, let me just last question about the introduction. In the thesis you mentioned, you provided an exploration of the main techniques related to the DynaML or embedded AI field. And you also explore topics like quantization and prunings. Then they were not then explored in the thesis.
Yeah.
So why, and what is your opinion about those topics?
Yeah, so you're right that like a lot like quantization and pruning of models is like really a cornerstone technique in embedded machine learning, and I'm sure it would, if I had more time, it would also have been a bit of this presentation. I think again that I maybe thought that the field was kind of saturated with these contributions. Like there's a ton of people that are working on quantization, doing it in different ways, like different number of bits that you want to quantize to, down to binary, to different data types, by layer, channel by channel. So I guess my thought on that was just, as I sort of presented in the beginning, that there's a lot of people working on this, and perhaps it's like better to try to look at another aspect that's relatively underexplored for our field and see what innovations we can actually do there. Because I think like some of the contributions that I have here, like the data set and this data awareness for like making it easier for people to use embedded machine learning, that matters a lot more than like some like small accuracy improvement or a small resource consumption reduction that you could achieve by quantizing to some layers to 4-bit instead of 5-bit and so on. That might be a hot take, but yeah.
Okay, so then I mean I have a question from introduction chapter. So there you are this page 7 or 8. You are comparing the embedded ML to cloud approach, and one of the things you claim is that like the embedded ML has higher reliability because there are fewer potential points of failure. But do you think there are maybe some disadvantages of embedded ML as well when it comes to reliability? Because I personally think this is only one part of the picture.
Yeah, I suppose it depends on how you if what your alternatives are. I think when I'm writing this, I'm sort of looking at these two alternatives, that you want to run some in machine learning application in a device that has an embedded system. Then you can do it either by putting a radio on the embedded system and you communicate with a cloud. Then my argument is that once you introduce this, then you have a chance that the radio fails, you have a chance that the internet connection fails, you have a chance that the cloud server is for some reason down, unable to provide. And in that way you have like many more points of failure than if you're just relying on the processor of the embedded system.
But like if something happens on that processor, then because in the cloud I have also duplication of all sorts. So if something fails, there are things to replace it. Whereas on the other side, it may be more difficult to achieve this, right?
Yeah, so I suppose you could come up with some applications. Say you have an embedded machine learning system that's figuring out data samples to save for some, like, I don't know, creating a data set later to train something. Then if you stream that data directly to the cloud, then you're going to have all the benefits there of like data replications, you're going to have backups and so on. Versus if you just store things locally on your embedded system, then you're not necessarily gonna have these backups. I'd maybe argue that like then like you might also just perform the machine learning still on device and then like just because you're performing embedded machine learning on device, this doesn't mean that you can have a radio on your device and send like the important samples or whatever you figure out to the cloud for backup afterwards. Yeah.
Yeah, same page, actually, page 7. And actually, a follow up on this. So there is a claim you start with power consumption.
Yeah.
Saying that it's possibly better to compute your neural network locally without the need of having a radio.
Mm-hmm.
And then you say that almost 90% of the energy of a cloud-based ML system is actually sending in and out.
Yeah.
So how does this compare with how much energy you actually consume when you have a system that is totally independent? Is the 10% actually what you spend to do computation locally for machine learning, and 90%, this 90%, is it from the perspective of the server or from the?
That's from the perspective of the embedded system.
Okay, so in principle, if I wouldn't use the radio, I would consume 1/10.
Of course, that depends on the application. I'm sure that it was that case for whatever source I put there.
Because yes, exactly. One of the things is that if I have an embedded system that gets data and send them to the server to do some machine learning processing, and then send them back to me, then I'm not doing the machine learning processing. The 10% is just collecting the data, packaging it up,
That's fair. Yeah.
sending it out.
Mm-hmm.
So if you move the machine learning process locally, so if now I have a full neural network running,
you're going to have a lot more processing locally,
and I don't have the radio,
Mm-hmm.
then how does this power compare? Because
I can give you
it's
exactly.
sure that it's going to increase quite a bit from just getting some data from a sensor and sending it out. Then clearly most of the power is to drive the antenna. So they have a take on this.
I'm sure I can have a take. I mean, of course, I can't give you exact numbers right now because that depends on the hardware that you're using and the processor that you're using and so on. But I think I'm quite sure generally that when you look at the figures of like what consumes power on these devices, then radios and like any sort of communication really dominates the energy consumption compared to processing. Maybe if you have a display on something that also consumes a lot of power, but like maybe that's out of the figure. But I guess the main takeaway is that processing is I'm willing to almost say 99% of cases cheaper than doing the radio transmission to send data off the device. But of course, there can be some edge cases where this is not the case.
Because some of the very strong arguments like security and privacy. That's a very, very strong argument. The fact that latency becomes deterministic.
Mm-hmm.
Maybe the power argument is a bit fluff in general.
It is a bit fluff in general because it's always application specific.
Exactly.
Yeah. So if you want to be completely sure, then I guess you need to create two identical systems and
measure
it. Yeah.
I'm fine with the introduction, then we can switch to you.
Section. Yeah, thanks. Yeah, let's start with section 2.
Okay, so let me share a general opinion about the chapter number 1. It is an interesting survey. At some point, I missed the specific aspect about predictive maintenance, since it seems to me a general. So the flavor was about predictive maintenance, but the impression was that it was related to a survey about ML. Such that at some point you cite data sets which are not related to predictive maintenance and so on and so forth. I would like to start about the technology. So from a technological perspective, you list some of the technological solutions starting from tiny devices going up to the Raspberry Pi or Google Coral, which are not tiny. Which is the perspective you have in terms of architecture about a predictive maintenance system, technological architecture?
But so what sort of embedded machine systems would be used in that?
No, I would move to the architecture. So not just a single device. So then we could go to a single device, but which is the architecture of the system that you would suggest to deploy a predictive maintenance system?
I think that depends a lot on the system that you're doing predictive maintenance on. I think if I was going to create like a predictive maintenance system for some machine, then the first thing I would try would be to, like, first of all, see what data I have on the device. Maybe there were some sensors installed in the system. Maybe I can install some, and then I would probably start. If I had free reins to do whatever I wanted, start with trying to develop models, even on my computer, and see what sort of like what size I could get a model to perform at some given performance target that I want to reach at, and then I would decide on the system later on, and then it becomes so application specific again. Because
So let me be more. Let me rephrase my question. So let's assume that you want to do predictive maintenance by using, for example, MEMS accelerometer. So you are measuring vibrations.
Yeah.
You decide which is the sample rate. You decide the number of channels, and so on and so forth. And then you have to decide how to design and then put in place a system encompassing going from tiny devices going up to cloud, with even something in the middle. Which is your opinion about that, and how would you design that system?
I suppose you can also have like a lot of different considerations in here. I suppose the most embedded machine learning system like that would have some sort of device listening to these vibrations, and perhaps doing anomaly detection, figuring out when vibrations seem to be off from normal. And then whenever it figures out that vibrations are off from normal, then it would send some signal off the device to alert maintainers or something that, oh, hey, something is not working as intended right now. But there's a lot of other architectures you could consider. There's also oftentimes this approach of doing cascading architectures, as we call it, where you sort of use the models that are on the embedded device as a sort of first filter. So maybe you can use embedded machine learning to figure out that 90% of the cases are so normal that we do not need to analyze them using a more intensive machine learning system. But then the next 10% you can send off to the cloud, still saving a lot of energy because you're sending way less information to the cloud, process that there, and have a lot more resources to figure out if there's some anomaly in these samples. That's sort of two system architectures, I would say. Is that some sort of what you're looking for?
Yeah.
Maybe related to, how do you approach designing these things? In this chapter, you go over different systems, layers, and the options for them. But if I want to start to designing the application infrastructure for predictive maintenance, like where do I start? Like, do I first pick the model, hardware, application specific data, like how does how does the steps go?
It's a good question, and it can look very different from place to place. I would say generally I would start with the data. That's the hardest thing to sort of get after the fact. If you want to create a predictive maintenance systems, based on machine learning at least, you should ideally have like some data captured over a long period of time for whatever machine you want to do predictive maintenance on. Ideally also have labels that tell you when things are actually working and when things are not working on this machine, so that you can give some labels to this data. So if you don't have that, I suppose that's where you need to start. Like as with all machine learning systems, you need some data, and I suppose that's also where most organizations sort of fail, because they want to do machine learning, but they did not gather the data that's needed for it. When you then get to the question of like whether or not to design the model first or pick the hardware first, I think I'd say if you don't already have embedded systems deployed in your factory, which I suppose you oftentimes have, because they're also solving a lot of other tasks here that are not necessarily related to machine learning. So it might be expensive, or it might be like taking a ton of work to go and replace these old devices, and then it probably makes sense to look at what resources do you actually have left on these devices to introduce some intelligent systems there too. And then I guess you're in the area where you have some resource constraints and you need to design a model or a system that works as good as possible within these resource constraints. If you are in the unlikely situation, I suppose, that you like can choose freely what embedded system you want to use, what hardware system you want to use, then I think a better way to start would be to figure out what sort of performance do I want to reach, what's acceptable in my application, and then at that point start designing or testing out machine learning systems, seeing what sort of resource constraints you can reach, and then get whatever is the cheapest device that fulfills the requirements that you have for your application.
All right.
So there is clearly very much application specific. Industrial setting where you want to look at a big machine, then you can wire things, you can use as much power as you want, or it could be on a plane, or it could be on a car, a small robot on the moon. So it's very specific. But you state somewhere here that it is desirable in general, or even essential, to deploy the machine learning, the predictive machine learning directly on sensor devices.
Do you have a page? Or...
Page 15, way through the page. And I like to ask, and that makes sense in some context, but I like to ask you maybe to give us an impression of what a system that is based on this, where you have a small neural network very close to the sensor would look like. Wouldn't you anyway need a network to connect all of this together? Because very often in predictive maintenance, you have multiple sensors around. So the input of your neural network is not just one MEMS accelerometer. Usually you want to measure multiple things at the same time, and then your machine learning is there to identify patterns that you wouldn't be able to identify with an in-range kind of threshold. What would happen in a car, for example, say if the sensor is out of range, there is a fault. We use machine learning because we want to learn from multiple point patterns that we are not able. So you would still probably need to connect these together and exchange information about the other sensors. So I know that it's very application specific, but maybe to give us an example of what a system would look like. There's a central unit, what moves through the network, what is in these sensors plus machine. We have a distributed model. We can do some computation locally, and based on the survey, what did you see around? What is the best way for you, based on the assumption that you want to put neural networks on the sensor?
Yeah, again, very application specific, but we know that I think if you have say some sensor detecting the air quality somewhere, then I think you can probably create some machine learning system just like based on a single board where it has some sensors on it that enable you to get information about the contents of the air of different substances. But maybe the more interesting part is what you're hinting at towards the embedded system, now that the predictive maintenance system, where you perhaps have some big industrial machine, and you can't, like, if you place an embedded system one specific place on this machine, then you're going to miss, and you only have sensors there, then you're going to miss information about what's happening on the other side. If you are in a place where it's easy to capture vibrations well, then maybe you're not going to be able to get visual input still. In that way, I suppose what becomes interesting and what becomes the special thing about embedded machine learning here is that you can connect these sensors via some like local network connection. I would say that is still different from sending data out on a wider network, such as the internet or something like that. And that way, you still preserve a lot of the privacy and security, because I mean, now people can intercept signals if they're standing near the machine, and they can plug into the cable that's running between your sensor and your embedded device. But it's not like they can intercept the connection between your factory and some cloud system.
Yes, but which application do you see where the sensors are actually connected through the internet? Which kind of machine are you doing predictive maintenance that it is so large that I need to have the internet in between?
Usually any application where you're doing the main machine learning processing on the cloud. Yeah. And I don't think that is that abnormal.
Yes, so you would consider as embedded machine learning also if I have a small computer in my factory where I send all the sensors there? Because
I would not consider it embedded machine learning, but you're right that some of these points that stand out for embedded machine learning are not exclusive to embedded machine learning, but they're sort of like the comparison point between that and a cloud alternative.
So what would be then the advantage of moving the computation to the sensor? If anyway I need to collect data, okay, leave the network out. If I still can get just the sensors and a small IoT node streaming some bytes to a small computer I have in my factory or inside your car, that then collects all the data and does in one place computation. That's also an embedded system. So what would be then the advantage of try to distribute the machine learning processes to the nodes themselves, to the sensors themselves?
I mean, I suppose still a lot that you avoid a lot of data movement, which can create latencies and like can create a lot of energy consumption. If you have these devices already deployed in your factory, it can also decrease cost, because now you don't need a separate infrastructure in order to actually run these machine learning systems. Maybe we're also living a bit in like maybe you're also not in a dream world where it's super easy to hook up your sensors that you already have available to a larger system that can be a server in your backyard or something like that. So I suppose in some situations you just only really have the option to run the machine learning there directly at the sensors. Yeah. And I mean, then I guess I also still want to point to the energy consumption, because I mean, now we are sort of talking about it as like on a factory floor, but you can also want to do predictive maintenance in many other places in remote areas. And this is sort of where, where did I put this? And this is sort of where this idea that when you do embedded machine learning, you are able to rely on other power sources than the main power becomes like really great, because good luck deploying a large machine learning system in the middle of a forest or in a jungle or something like that. Then you need some small devices that can run for a very long time on a battery or some energy harvesting device to actually be able to do anything intelligent in those areas. Yeah.
Could you please go back to the slide number 14?
14, yes. This one?
No, sorry, that was not here. Maybe before. 7, sorry.
7, yes.
Do you-
Almost 14.
Keeping in the path of the system and the interaction between embedded and cloud, which is the role and how do you see the future of the edge computing in this path? So,
Can you repeat?
edge computing.
Yeah. So how do I see the sort of continuum between edge now, like embedded edge and
Cloud.
Yes. Yeah.
Something in the middle.
Yeah. Yeah, I mean, you could split it up like that. You could split it up into something that's like way more granular, having different types of edge systems. I guess this sort of touches on this idea of cascading architectures that I also discussed earlier, that you can have an embedded system that offloads like hard data samples that could be to the cloud, that could be to some desktop PC or something like that. I guess there's some advantages to like having some edge processing available in that, like you can have you can preserve some of the privacy and security by keeping stuff on a local network, as we discussed, and processing hard samples there as an alternative to doing it in the cloud. Is it sort of like that you're looking for?
I was wondering whether you see advantages or disadvantages, or you're absolutely neutral about this
Again,
the computing continuum.
Yeah, again, as you say, I think it's a continuum. So in embedded machine learning, you have like really low power consumption, but you also have very few resources. And I mean, then you can offload hard samples or whatever your application is to something that's like has a little bit more resources. And if that's enough, then you can have the advantages that provides. But if you need the more resources, then you also have some cloud services available. But of course, again, with the disadvantages that has. And I mean, you could also have something in the middle between that, like say you have some NVIDIA Jetson Nano or some Raspberry Pi that can take care of like a little bit harder systems, or harder samples. So I think that's, as you say, just a continuum. Like you go as far up in the system as you need to, I suppose.
Is it related to the scalability issue that you mentioned, since you are adding a further level of heterogeneity in your system? How do you see that?
I suppose it could add problems. I think mostly for the devices that you could still consider like embedded devices, such as Raspberry Pis and so on. The thing is, I think once you get to a certain scale of a device, like maybe even a Raspberry Pi, but maybe on a bit larger device, you get to a point where you are going to have your typical operating system running on this device. And this operating system is going to provide you a lot of libraries that sort of like hide away all the ugly features of the heterogeneity of the device, and just provides you with a bit of a nicer interface, that if you're supposed to run an embedded machine learning model, then you're using these libraries that are part of the operating system, or can at least be installed on top of the operating system. And in that way, once you get past a certain boundary, I don't think you have the same scalability challenge. It's not that if I create a machine learning model to run on my computer. I can run it on yours. That's also a MacBook, but I could probably also easily port it to Pinar's laptop, just because we have these interfaces or stacks that we can build on top of that ensure that we do not have to worry about all the ugly details of these devices being different.
Maybe, I mean, this question may be more general, not specific to predictive maintenance, but just to follow from previous discussion. So when it comes to this embedded domain, then can you, like, is it realistic to expect to have this type of more generalized or standardized tool sets to use to build applications or applications with machine learning on these microcontrollers or other sorts of devices on that level, considering that their resources are so limited that to get the best possible performance, you may need to do specialization regardless.
I get your question. I think it's a question that, if it's probably again application specific, but maybe even in a general sense, it has not completely been answered yet, and in that way, it's maybe a $1 million question. If there is a future to this hyper optimized embedded machine learning where you sort of throw away every abstraction layer to get all you can out of the resources that you have available, or whether it's worth, I don't know, maybe not deploying operating systems on our embedded devices, but at least having some small containers to make it so that the systems you create for one device can actually be taken and ported to another. I think maybe a third alternative to that is to do much of these abstraction layers on larger devices, so that the tools we use to create embedded machine learning systems are perhaps creating these machine learning systems in an abstract way, and then this tool can sort of automate the way that this model has to be changed in this way and use these particular operation when it's deployed to this device, and deploying the same model to this device could be, maybe there's a sort of what you call it, step-by-step way that you can do that and program that into a tool. The question then, or the challenge then, of course, becomes that you need to have such a tool, and that tool needs to be able to support all of these different devices, and that's definitely also a big technical challenge.
Yeah. So to follow up a little bit on this, on the hardware, you have a section in the survey where you analyze the compute.
Yeah.
2.4.1. You don't need to go there. So there you make some arguments to say, okay, I'm looking into specific things, and one of these, one that actually, a couple that actually I have some questions, and maybe I would like some clarifications about flexibility and usability.
Yeah.
So I think that there are two. It's a bit of a trade-off. This is a well-known thing. If you want to be more flexible, then you're going to have an operating system, and then you're going to have more abstraction, and then you're going to lose performance. At the same time, we're talking about embedded machine learning, where you want to use the last kilobyte of your memory. So you would like to have a bare metal system where you don't have anything.
Yeah.
So based on the analysis that you did, what do you think is the right direction here? You also go down and mention different technologies: CPU, DSP, FPGAs, GPUs. So in the context of predictive maintenance, which the survey is about, but also more in general about TinyML. So what's the direction that you think we should go in research? What's the right thing to do here? Should we think about abstracting and have a more easy to use, something that you say in your paper is not only an academic exercise, so something that it is easy to use and accessible, but then of course you pay the cost of wasting resources because it means high abstraction, or
Yeah.
or we should go into saying, okay, for embedded, the right thing to do is actually go down as much as possible, go bare metal, use no abstraction, and all of the complexity needs to be into the tool chain that creates and it is adapted to the different targets that you have, which are quite a lot. You list here FPGAs. I mean, this is very different technologies from targeting an STM32 microcontroller or something that generates hardware that goes into an FPGA. So what's your take here? What's actually realistic? What are the real trade-off?
That's a very good question. And of course, I don't have I can't give you the perfect answer, and that's an opinionated one.
Yeah.
As I express in the presentation and the thesis, I definitely think we need some way to scale the current approach, which involves a lot of manual engineering. I suppose going the way of having sort of tool chain on larger devices that generate these very high efficient models for devices would probably be where I would put my money if I was to choose one. I think you're gonna end up getting better performance on most systems because again you're not wasting resources. I suppose the problem becomes less of a technical one and maybe more of a business problem, that now the task of supporting devices is not really done by the device manufacturer necessarily, but by whoever is working on this tool chain, and it's not up to the device manufacturer to sort of make sure to implement these abstraction layers on the device.
Sure, but I was more asking from a technical point of view more than of course, a business point of view. Where you think it's right as an expert of the field, where you think it's right to draw the line between abstraction. So should I stay very low and say, okay, the tool chain should do everything and know the architecture up to the instruction set, so the binary and the hardware available, so the tool chain knows everything about my target? Or it is fine to draw the line a bit high and say maybe some common framework that some basic operation needs to be there in order to be a target, and therefore it's easier from a tool chain point of view, or it can be even higher and say we just run some.
I'd say the first. I think that's the way to go. Yes.
This would kind of bring a little bit away the term of usability.
Yeah, but then the idea of usability would sort of be solved by this tool chain that you're describing, that people would run, and then I guess that abstracts the idea that you can have different processor types, and you still write the same model, but the tool chain takes care of how this works with a particular processor or accelerator.
Common interface, a common agreement between the basic operations needed by a neural network, that they could be implemented in different ways, something similar to an instruction set, where you abstract away the hardware a little bit, but not too much. Could that be helpful in this field? Something specifically dedicated to match the basic operation needed by a model?
I mean,
do you know any of these approaches that maybe have been used?
I know that some of these approaches for sure. Like one of the most popular ways to deploy embedded machine learning right now is actually done by sort of such an interface, like you have this TensorFlow Lite micro interface that is a library you deploy onto an embedded device. I guess the embedded device has to accept, like, be able to use this library, but that is then like that runs as an abstraction layer, sort of like taking a model and then translating that to the instructions that actually need to be executed on this embedded device. So to some extent, that is what is being used right now. I still at standing here right now, I only see advantages in taking that tool chain and making all of that stuff be done offline on larger computers, and then what you actually deploy are the real instructions that need to be executed. Yeah.
Kevin, page, where is it? 29, you mentioned on-device learning.
Yeah.
Could you say a few more words about that? How is it relevant for this task?
Sure. Yeah, I already sort of introduced that with embedded machine learning, we very typically create our model and on a larger device, and then we deploy it onto an embedded device. Then typically there's no way to retrain this model at this point. It's set in stone, and that can become a problem in some scenarios where you have the environment where the device is deployed. It could change. You can see that if you deployed some kind of face detection algorithm right before the pandemic hit a couple of years ago, then that would probably not perform very well as soon as everyone starts putting on face masks. And then you're in trouble if you've deployed all of these systems to embedded devices and you have no way of changing them. Another reason you could want to change the model after deployment is if you want to do some sort of personalization. Like I have a watch here that I use to track my sports and so on, and it can sometimes track when I'm starting to run or whatever. But it could be that people have like small differences in like how they move when they do whatever and so on. And you could use, like it would be beneficial for the model to be able to be trained on some personal data that could improve the model's accuracy for whoever is using it. So that's two use cases where you would like to be able to change the model once it is deployed. And that's what the idea of on-device learning is then, that you would like to be able to, in some way, adapt the model once it is actually deployed to the embedded device. It's not so much you want to train it from scratch. I haven't seen anyone actually want to do that. But there's a couple of different approaches to that. You see, the main problem with training a machine learning model on an embedded device is that in order to compute these gradients that you need to train these machine learning models, you need to store all the results that happened throughout the entire model. And in these embedded devices, we just very often do not have enough memory to do so. So there are some ways that people can try to get around that. This range from adding a single layer at the end of, say, a neural network model that you can then train on the fly. Now you only have to save the outputs and not the outputs of the entire model. And then you can train the last layer to sort of be the personalized layer. Some folks have also proposed training models by just adapting biases. That gets a little technical, of course, but it's possible to calculate the gradients of biases without actually knowing the activations. And in that way, you can actually do some training without saving all of these results. And then there's
I do see the point, but technically, what typically happens is the fact that you can adapt, you can fine tune, you can personalize, and you can also try to squeeze the amount of information that you propagate that you have to save. But if you, in particular, if you're dealing with neural networks, if you just update with one or few samples, you typically end up in catastrophic forgetting, meaning that at the end, you have to deal with the batches of data, which is typically the main bottleneck when you do on-device learning, because at the end, you have to keep a batch of data.
Yeah, that becomes really expensive in terms of memory as well.
Yes, absolutely. As you mentioned, you could resort on KNN, but in this case, the problem is further emphasized because there, unless you have a feature reduction model at the very beginning, the amount of data is exactly the amount of samples that you process.
Mm-hmm.
Do I have time for just in this direction one more question? You mentioned personalization, which is typically very good, or adaptation again, which is very positive.
Yeah.
But on the other way around, you might end up with drawbacks with personalization adaptation, because if you personalize the model, which at the end is worse than the original model you had, then the personalization didn't work or is not worth to be
sure. Yeah.
This is particularly relevant in the scenario of predictive maintenance, where if you have a system that you are trying to approximate to the model and the system slightly evolves over time, you are just learning the evolution and hence not being able to detect that there is a change. Which is your perspective on that?
That is a fair point. So I guess that depends completely on like what kind of failure modes you expect to be able to see in such a system. You're right that if you have a system that's supposed to do predictive maintenance and you introduce some sort of like on-device learning on that, and that causes the machine learning model to sort of learn that the device is sort of deorientating over time, then it might not detect the right thing that you wanted to detect. That at some point it's time to do maintenance on this device because you've sort of just learned the poor performance. But yeah, but on the other hand, I suppose you could also easily end up in situations where like this drift in like maybe let's say you have one machine that's producing item A, now then it gets changed to producing item B. Maybe that has some different signature on the data, and errors are still going to look like widely different in this world. And then I suppose it would be beneficial to have some on-device learning to learn that now the normal samples actually look like this, and you don't get a lot of false positives because you're now producing another item than you were when the model was trained.
Yeah, I see the point. You're right. Take into account that at some point, the drawback or the main challenge of on-device learning will not be the amount of memory that you have to store, but the availability of supervised information.
Yeah, that is also
like cases in which you cannot assume that you keep on having supervised information to train the model. That will be.
You need some human in the loop sometimes. Maybe the device needs to register this was a challenging sample. I need someone to label this for me to get an idea. But I also don't think that's impossible. If we take the idea of like a watch again, if like it could ask for feedback, did you just run? Did you just dance or whatever? And it doesn't need to be harder than that sometimes to collect this supervised information.
Well, maybe we should move to paper B. I'm happy myself. But...
Yeah, I can start with questions on paper B. So first, a higher level question. So how do you evaluate how good a data set is? I mean, obviously you have a methodology in paper B, but is this generally applicable, or did you have a systematic way of approaching that evaluation, or it was just based on the application case?
So it's not like I know of like one set methodology to evaluate data set qualities, but I could very well imagine that it's not the same for every data set. Like we talked a lot about label errors as sort of our measure of quality in this data set. But I mean, very simply, this would not be applicable if you have an unsupervised data set without labels, then you're not going to have any label errors. So that is not a way to judge quality in that data set. I mean, label error rate also doesn't speak anything to how good the pictures in our data set are, and whether or not it's diverse, whether or not it's just not a data set of the same image repeated 6,000 times. I don't know. I could try to come up with a bunch of different metrics right now, but maybe that's not the point. But for sure, it's not the only one. And I do actually think that there are some frameworks I've machine learning. I don't think there's anything at the scale we are at right now, and that's perhaps some future work to. Because I think it's especially interesting, which so probably a bit of a derivative of this question that in reality, like data has turned out to be like a big challenge for a lot of embedded machine learning systems, and out there in the wild, you have a lot of people like trying to create the best data set they can for their application, and being able to create some kind of tool that could take a look at a data set that someone has created and be able to give actionable insights on like what's the first thing you should do to improve the quality of this data set. That could be really useful if it is fix label errors, add more samples, add more diverse samples, or something like that.
Or maybe putting it the other way around, like when, like at some point you need to decide, this is the data set I have, but this is not good enough, so I need to create something else. And how do we create that trigger from this? Yeah, basically deciding the existing ones is not enough, so I need a new one. I mean, I guess you mentioned some of these with the sample size and the label quality.
Yeah.
So,
I mean, I suppose the main way you figure out that your data set is not enough is if it just seems like it's impossible to create a model or a system that reaches like the accuracy on the application that you want to create, and I suppose that should be the trigger to like starting to work more on the data set side again. Yeah.
all right. I have more specific questions, but
Yes.
later. Yeah.
I mean, on paper B, table 3.1,
Is that in here?
I don't think so.
I have a bunch of extra slides down here. How does it look?
The table about model suitability for TinyML.
Is this these ones?
No,
it's
it's
a
a table 3.1. Maybe.
Just
See if I
open
can
it,
find it.
just open it in the pages. Page 44.
44?
Maybe 72. Actually.
It's this table you're looking at?
Yes.
Okay.
So the
I
last
think I
one,
have it, but okay, we'll just talk about it.
if you have it, put it up for the audience.
I think it's 72. Yeah.
No, that's
Oh,
not
no.
the one. Should have this ordered somewhat. Wait, wasn't
Yeah, let's just.
okay? Let's just talk about. I think it was in the presentation, but yeah.
So there is the last column. The last column is suitability for TinyML of the data set. So the first sub question to my question is, where does this come from, and how did you decide that yours are suitable together with the parent, the visual wake words, while the other two are not suitable. What does this?
Yeah, good question. Perhaps the suitability is the wrong word in this context. It's rather that whether or not the data sets are designed for an embedded machine learning purpose. So, like I described in the presentation, we have a lot of data sets out there in the wild that target widely different applications than those we target in embedded machine learning. The point of this column is that wake vision and visual wake words is specifically designed with the intention that there should be a person detection data set. There's a person label and there's a non-person label. Versus for the other two data sets, there's a person label out of like 100 other different labels, which I suppose would then become a no person label, with the risk that maybe there's also a boy and a girl and a man label and so on.
Sure.
Yeah.
How does it make it unsuitable? What are the metrics that you took into account when you decide that the Pascal VOC, the CIFAR 100 are unsuitable for training small neural network, tiny ML?
Again, I would say it's probably better called that it's not designed for it, but that also means that there are some parts of the data set that might be unsuitable for like creating the best sort of models.
I understood your answer that you said it was not designed for it.
Yeah.
So when you design it for it, which metrics do you take into account to say, I design it with TinyML in mind, or I design it with large model running on a server in mind? Then of the day is a set of images with labels which you can pre-process and scale at will. Of course, you have a very good argument about the error rate. So that's in principle applies to any data set. The better the data set, the better the data set. The less error there is, the better it is in general.
Yeah.
So what are, in your opinion, the metrics that says, okay, this is very good to train TinyML, while this data set is actually not very good? So if I would start today designing a new one, as you say, then what should I keep in mind that I shouldn't keep in mind when I design a generic one?
I think to add on that, one thing that we and this visual wake words dataset make sure when we are having a binary classification between person and non-person is that then these classes are balanced, for example. So there's an equal amount of person and non-person labels of samples in this dataset, versus if you take some of the other datasets, and they're not here, but then you might have 10% of person samples in there, and you might have 10% of something else, and something else, which means that you're either going to have to remove a large part of the data set as a pre-processing step, or you're going to have to make sure that like it's weighted more in the evaluation that your model is able to detect people, because otherwise you could really achieve like a 90% accuracy by just saying that every sample is not a person. So that's, I guess that's like a bit of holes you can fall into if you don't have a data set that's specifically designed for the purpose that you're trying to adapt to this use case. I think there's also some intricacies about like what is considered a person in different use cases. For example, I mean, there's a lot of things that's hidden away about the decisions we made for wake vision, like whether or not, if you have a shoe in a picture, is that considered a person? If you have a hand in a picture, is that considered a person or is it not? And when you have a person detection data set and you sort of have an idea of what use cases or what applications this data set should be used to, I think you are better informed about what is a good decision to make for that data set versus when you have a data set that's meant for something different, you don't have that information, and you might end up with some unfortunate choices as to what is labeled a person. And
That mean that, I mean, this goes back to the statement that you make that small models are more sensitive to error. And how would the labeling criteria that somebody takes make something unsuitable for a small model? Because maybe I'm saying, okay, if there is a shoe in the picture, a foot in the picture, then I say there is a person. Then in principle, it's because I expect that my model would identify a shoe in the picture as a person.
at least it should.
Yeah. So this is a labeling criteria.
Yeah.
We may agree or disagree depending on the application. Which is bad for small models, but it is good for large models. So, because the question was, what should I take into account when I design a data set that it is suitable for TinyML? And your answer was, you should take into account that the balancing. That's okay. And then what is the criteria of labeling? If there is a shoe or not in the picture, how does the last one enter the picture here? This is more like what you want your neural network to identify.
Yeah, but I think that's like, it's also important to consider this application when you're designing the data set, so that the labels you create are correct for that application. Like
it goes back to the argument of correctness, the error rate.
Yeah, I suppose you could say so. And following up on that, like what we learned here is that our criteria when creating data sets for embedded machine learning models is perhaps also that you want to like have high quality data. So like if you have a choice about, like we saw before with this green, yellow, and red data, then you'd prefer to perhaps pick the smaller data set that is of higher quality for embedded machine learning models.
I will follow up on that later, but
I have a question which is different, but this slide is particularly interesting because in principle this holds for any machine learning models. Obviously, the higher the quality, say, of the data set, the larger the accuracy. Obviously, you need to scale the model according to the complexity of the data set that you have. But in principle, that's not related to just TinyML. It's related to any machine learning model.
Yeah.
This is for sure relevant. But my perspective about that I share you my personal humble opinion is that model is suitable or not. A data set is suitable or not depending on the size of the image, because if the image itself cannot be stored in the memory, that's unsuitable. But it is difficult to match the fact that a data set is suitable for TinyML. So that's
because you could also do a lot of pre-processing, I suppose. If your only problem is that the image is too large, you could.
Yeah, you can scale it down, but that's also even for this one. So this holds for everything. But my question, which is a concern, is about the fact that you mentioned that you formulate this is a binary classification problem.
Yeah,
person and not person. Being a devil's advocate, I would say that that's not binary classification. It is technically a one-class classification problem in which you have information about just one class, which is a person, and then you want to identify everything is not a person. So how do you match this with your data set? And what do you think about my opinion? You could say you do not agree, absolutely.
Yeah, I guess that's that. I don't know if I agree. Like, there's different ways to formulate these problems. Like, if you count the unknown class as a person, I don't know, but like, if that's just a question of like semantics or what. But can you say it again?
Yeah, if you formulate the problem as something and not something,
yeah,
it is not a binary classification problem. It is because if you have something and not something, you are somehow putting a semantic about the concept of not something.
Yeah.
But in principle, that might not be correct because you might have something different than
You might have something different that is
Okay.
not included in the not
exactly, which is again, it is the non-something, which is again not person. If you are just putting a boundary between person, not person, your classification problem, you're not taking into account the fact that you might end up with different non-person data, and this would force you to create some sort of hypersphere around the concept of person, and everything is not within the hypersphere, then it is a person. And this might also end up with a scenario in which you don't have to balance, to force the balance in between person and not person, because you don't care, you just focus on person, and which is super useful to have a high quality person, but this might help you in saying, I do not need to specify the concept of not person, because in principle, everything is non-person, but those who are person. Do you see the point?
I see the point. I'm not sure I agree that this means that you shouldn't have a labeled data set. On the top of my feed right now, I think that depends on how you decide to treat this unknown class when you're training your model. Like if what we've done is here, you have two output classes. You have person or not person. I don't know. Then I guess I'd still treat it as a two a binary classification, with acknowledging that it is really hard to be exhaustive about like getting enough samples or getting enough examples of the non-person class to make sure that you can't find something new that might confuse the model. And I don't know if what you're fishing a bit for is that like there's also other ways to like train these models where you sort of change the problem from a classification problem to sort of a regression problem where you are giving sort of a confidence score, so you could say, of how likely is it that this image is of a person. In that way, I suppose you could have it as like a single class problem where it's you generate a high score if it's a person, you generate a low score if it seems to not be a person and it seems to be not around this cluster.
This is not a regression, but the idea is that you are somehow defining the concept of person, and in this way, say, the larger the amount of person, the better, and then you don't care about the rest, in the sense that you are just using the rest as a validation and testing, because at the end, during the learning, you don't need the rest. Mm-hmm. This might help you in putting a further emphasis on person, because at the end, this is exactly the topic that you are interested in, so the task you are interested in.
Yeah.
So can you go to slide 37?
37. Yep.
So here I have a few questions to start off with. So you show that, okay, by using your data set, you can achieve higher accuracy. But as someone who is not a machine learning expert, like, is this 1% worth creating an entirely new data set, considering the amount of work you put into this, playing the devil's advocate?
Yeah. I mean, I guess that's a question you can discuss. I think that depends on like the scale of what we see this application being able to do. If you're at a scale where, I don't know, you're working with digital assistants and you're detecting keywords and you need to design Apple's Siri, then I would say it's 1% is going to do a huge difference. And it's worth for them investing billions of dollars into. If you're targeting some obscure application that is not safety critical or anything, then I suppose like it could be less worth the time. Since this is sort of the primary vision use case we see right now in embedded machine learning, I would say that it goes a long way to have this improvement. I'd also say that, as I mentioned while I was talking about this slide, we try to be quite fair to visual wake words when we are comparing the two data sets here. So we trained them for the same amount of training steps by the same amount of images. So this is not necessarily giving you an idea of where our data sets saturate. Perhaps you're able to like reach more than a 1% accuracy improvement if you train on our data set for long enough that it's sort of proportional to the size of the data set.
I guess that was my other question on this. So you said same amount of steps. Is this strictly time, or can the steps be of different lengths when you are training with your data set versus the other one?
I believe in this experiment, data was mostly like pre-processed in the same way, so that images of the visual wake words data set were and the Wake Vision data set were all cropped or rescaled or white space added so that it fit a specific resolution of like maybe 224 pixels and on each side. So it probably takes the same time, but the steps refer to how many batches run through the training algorithm. And so no matter the data set, the model has seen just as many pictures in this experiment.
Maybe like again on the same topic, I'm wondering if it would make sense to add this evaluation of which data set is better, the also resource consumption considerations or resource awareness considerations, because if the newer proposed data set requires you to train longer time using more hardware resources to get to that 1%, maybe that should be accounted in the discussion of this is actually the better data set or not. What do you think about adding resource awareness as a metric to this type of evaluation?
I mean, I think since we are literally training for the same amount of steps here, that it is not that interesting. But given that you're not training for the same amount of steps and you have a larger data set and you want to sort of saturate your performance on this data set, then sure, then it would be quite useful to at least have an idea of what does it cost extra to get this performance improvement, and that plays into the whole sustainability question. And again, then we go back to the application dependent thing that like sometimes it's maybe worth training for a day longer to make sure that your model performs as good as possible. And sometimes if you have a simple non-safety critical application, then it's then maybe it's actually fine and you don't have to put that much effort into it.
We have 20 minutes left. So maybe we should
slightly more to account for the break. So
slightly more than 20 minutes left.
half hour.
Maybe I will skip my question of paper B and maybe see myself. No, maybe if you have more about B.
Just one. Oh, sorry. Could you go to slide 38, which is super interesting to me?
Yes. I can almost guess what this question is going to be.
So I'm trying to identify. Sorry, let's put it as well. Let please help me identifying which is the theoretical meaning about we are seeing. It's the theoretical meaning. So which is the meaning about this behavior, which is somehow counterintuitive. For sure, every time there is something which is counterintuitive, there is a theoretical explanation. So maybe it is related to the expressive power of the network, which is different here since you have different number of parameters. Maybe it is related to the fact that the larger the size of the network, the higher the probability to go into overfitting or to enter into local minima. which is your opinion about that? And did you evaluate the standard deviation of those accuracy in order to see if we are seeing something, but at the end the standard deviation is so large, so the confidence is so large that at the end what we are claiming might not be true?
So let me take the first one. So trying to explain why we see this kind of, you could call it weird scenario where a large data set full of errors perform better than a smaller data set that's of higher quality. That might seem weird. I think it was also weird when for a lot of researchers when they started experiencing this. Once we started to scale these machine learning models to really large parameter counts, by no means like a super expert in this, but when you have really large models that start having parameters, more parameters than you have samples in the data set, there are hints that you are starting to get into this area where you get a sort of benign overfitting that where people are a little bit unsure about why this happens. There are some theories that once you have all these parameters and more parameters than you actually have samples in your data set, then these models can sort of actually learn the errors that are as well exhibited in the training data and just learn to have one parameter that decides that just ignore this sample. And that might be why we see this behavior.
Yeah, because if you have large networks, in particular networks which are larger than the data sets, by definition, you enter into overfitting. Sometimes overfitting is you manage that. But this means that by definition, you will enter into local minima. So that's the reason why I asked you to see, if you computed the standard deviation about the bullet, the blue point that you have there, because if the standard deviation is so large, because maybe you were unlucky that you found a very bad models, but generally speaking, the average, the unfortunately was larger than the orange one, then that would help me in resizing my claim.
Unfortunately, I don't have that, and I don't think I can give you that right now.
No, okay, no. To know your opinion about that, if you saw strange behavior in this perspective. So some very, very unlucky case due to overfitting with respect to other.
Let me see. It's not exactly what you're asking for, but we did run this experiment across more than these two models, and this should also be in the thesis, right? And I do think that you sort of see the same tendency developing once you start having larger and larger models. It's not the same as running the experiment exactly a couple of times and seeing the standard deviation as you're looking for, but I don't know. I still think it's some evidence that like this is not just like getting unlucky or a single time.
Yeah, that is exactly the figure that I was looking at.
Yeah.
The interesting point there is pointing 4.9 million, where it is below the other one. So if you get somehow you would saturate, this means that you explore the full expressive power. That point with respect to the story, it's a point that's it is worth to explore. Maybe in the future you want to go there and understand what's going on. But
yeah,
yes, sorry.
So, I mean, I have also still a question about this chapter, and I don't mind not asking for the last one. Very different aspect of it. So you are, of course, releasing this data set for the general public, and the way you do it is in the form of files, if I understood correctly. So do you think, again, given your experience with these data sets, is that the best way to manage these types of data sets in the long run? Just files, like if I want to update this at some point, what are the consequences of that if everything is in files, including your labels, metadata, everything?
I mean, I guess that there is some challenge in that updating the data set might require you to like upload, remove, upload the entire file again, depending on if you have a system that's capable of like detecting the small changes in a file. But yeah,
Do you know?
Questioning what your other approach would be.
I mean, do you know, like, as I guess you have looked into like many of these data set offerings, like, are there other ways people like release these data sets, maybe rather than pure files, like a database?
Yeah, I was thinking of that. I suppose you could try to put these files or these images samples in a database as well. I'm not sure if I know some like system that's well suited for doing that and still making it really easily accessible for the public. One reason we did put it into these files was because by doing so we were able to quite easily take this data set and make it interface with some of these larger data set libraries that we see a lot of machine learning practitioners use, like Hugging Face data sets and TensorFlow data sets. In particular, TensorFlow data sets literally expect you to just download a bunch of files and then combine them in a way. Hugging Face is a little bit different. They might store theirs in a database like you are expressing about here, since whereas the TensorFlow datasets tool sort of interfaces with or gets data from the files we have uploaded. On Hugging Face, it's more that we upload our files and they store them on their server somewhere, and they may do that in a different way. I guess the answer is probably that practically worked. That's how we saw other people store their data sets as well. But it could, of course, mean that it's a little bit harder to update data sets along the line.
Do you have more question about paper B?
No, fine, thanks.
Okay, so maybe my single question about paper C.
Yeah.
It's about, I'll go immediately into the details, no general question. The fitness function.
Yes.
Can you take it out? If you have it.
Sure, I do.
Yep. The data-aware fitness function.
Yeah.
10, 4, and 5.
Yes.
What is run violation and flash violation? Is that?
That's how much we exceed the maximum allowable memory.
So it is. So the maximum allowable memory is how much memory you have.
Yeah.
So you don't want to go above that.
Yeah.
And you want a penalty if you go above that.
Exactly.
Now, the run violation, therefore, is the maximum memory you actually see it using minus the maximum allowable RAM consumption.
So
the maximum you see minus what you actually can. So it's the excess. Okay. And you want that to be 0, or can that go negative inside this formula?
It cannot.
Or
I haven't really explained much about the calculation of the violation, but the idea is that it cannot go negative.
So there is a little ceiling around that.
Yeah. So if you would calculate this RAM violation and flash violation, it would basically be a function that would taking the maximum of 0 and this equation you just said that like the maximum. No, the current consumption minus the maximum.
The excess usage, as you defined it just now, is the maximum I see over my full execution.
No, of 0 and the maximum RAM consumption over your use minus the maximum allowable.
Okay.
Yeah.
So it's always positive.
Yeah.
And you came up with this formula.
Yeah,
Based on experiment.
I suppose so. I don't think I gave like too much thought to it. The idea was just that like you want to give a penalty to whenever systems exceed these constraints.
Those two terms there, 4 and 5, are actually the core of the contribution, right? Because it's data aware, and you're gonna look for models that try to.
I mean, this is
reduce the memory footprint.
yeah. So like this fitness function is it's a core part of the contribution because this is what allows the search to actually find systems that are not exceeding resource constraints. Yes, I mean, if it's the core contribution, I think there's a lot of other parts about the system that also contributes to this search being successful.
Yeah. I'm just thinking that most of the results are about the RAM consumption and the flash consumption.
Yeah.
Saying that using your search leads to less RAM consumption. So those two terms are the ones that play the role here.
They're the one that drive the search towards systems that do not exceed the RAM and flash limits. Yeah.
So can you rephrase the point? Because I mean, here what you're doing here is that instead of putting some constraints, because then the exploration having hard constraints are difficult to be explored, then you're putting penalties. That's like the Lagrangian approach. That's what you're doing, which is interesting and for sure useful, but it's not novel, the usage of penalty term in the exploration.
No.
Okay. So the question is, where do you put? I mean, as far as understood, the novelty is in the fact that you are taking into account even the features of the data, like for example, resolution, sampling rate, and so on and so forth.
Exactly.
So that's the part which is because this is the typical approach that you have in hardware awareness, where what you do is that you are exactly doing this. You are penalizing. You are putting some soft constraints in the exploration of your architectures.
Yeah.
Could you say a few more words about the search strategy? Because I didn't find it in the thesis, and which is the technique that you use? Was it based on genetic or darts based, so something which is differentiable?
Yeah, not differentiable at this time. I'm working on it.
Which is now, so.
Yeah. No, but you have some details here. So it's a genetic algorithm that's
This one, an SGS maybe.
No, this is it's not that I took any of the like open source models. I basically like implemented my own for this.
Okay.
For this search, and it's based on this idea of like having a population, then you do tournament selection. Are you familiar with that term?
Yeah. That.
Okay. To figure out like for each generation which models are the most suitable, and this is where the fitness function comes in. The one with the highest score in the fitness function wins whatever tournament that it's in. And then the winners of the tournament are used to like generate new proposed solutions through mutations and crossovers of these solutions. And then there's some hyperparameters here of what I've been using.
In this part, the key aspects of NAS are typically surrogates that allows you not to retrain from scratch everything, because otherwise it will take ages.
Yeah.
Do you have something similar here, or are you required to retrain every time you design something new in your exploration?
No, the idea exactly with this paper is that we use this super net, as I would call it, or that is a mobile net V2 model, again, that we train once during the search. We actually train it once per the input data configuration that we use. but then you extract sub-architectures from this model that you retrain or fine-tune for a little bit to before they're evaluated. So in that way, you only really train this larger model once and extract sub-architectures from that.
Why didn't you use SuperNets, which are already available?
Why did I not use SuperNets that are
already available? And why did you implement your own SuperNet, which is on one hand is interesting, but it's it's a big effort.
Yeah. I don't know. I guess I'm not really like aware of any like SuperNets libraries or something like that that's specifically meant for like resource constrained devices or embedded devices. Honestly, like doing this again, I'd probably not have went with a mobile net backbone as to say, but something similar. Maybe you've heard of this MNAS net paper and this mobile search space that they're proposing, and trying to take some and using something like that would probably have been my go-to. There's maybe also some future work in not relying on these like search spaces that are kind of designed for mobile applications to even design embedded systems or machine learning models for embedded systems, because we usually have to end up like choosing very, very small parts of these search spaces that actually fit in our resource constraints, but trying to come up with new search spaces that are perhaps better fit for embedded devices and the properties that we have there.
Sorry, Landa, when I was talking, just
That's 15 minutes.
15. Okay, we are fine. No, that's super interesting topic, and I work in this field, so I'm super this. And when you combine search spaces, which are quite orthogonal in the sense of the resolution, the size of the image, and then the architecture, it's not easy to manage all of them in the same way. So did you see that some aspects are more relevant in others? Because at the end you have to converge in a minimum somewhere, depending on the starting point, depending on the way you put weights, you might end up with very, very different local mean. Did you see a structure in these multi-dimensional and multi space with multiple visions?
So let me see if I interpreted your question correct, but you're saying that like we have some data that we want to configure in different ways, and we have a model architecture that we want to configure in different ways, and these are not necessarily adapted in the same way. Like the architecture search space is very different from sort of the model, the data search space. So for that, I have some like hyperparameters that are sort of tuning the chances of like how what the probability is that we change like some data configuration, and what the probability is that we change some configuration of the model. The way I did it is that I sort of have like increases and decreases both in I divide my search space into categorical and sort of more it's maybe not numerical, but at least you can do a comparison. Ordinal, that's what it's called, yeah. Data, and I sort of split it out so that it's like roughly the same amount of chance to change the data and change the architecture. But for the architecture, we have these different stages we change. That's treated as an ordinal search space where you can either increase or decrease the size of these blocks by one. The same thing it is with the resolution. You can increase the resolution, you can decrease the resolution. When it comes to like encoding type, now I really only considered what is it called? RGB and grayscale images here, but that would be more of a categorical attribute where it's simply would be a random choice. Like it's not like you can order.
Are they part of your SuperNet or not? So did you create SuperNet to take into account the different configurations of the input, or they're exploring in an orthogonal way? Is the SuperNet just related to the architecture?
There's more than one supernet in the search. I think that's what you're fishing for. So there's like a supernet for each data configuration stored. Yeah. Do you follow?
Yes.
Yeah. Yeah.
This means that you are priori define which are the configurations of your data.
Yeah.
So this means that in principle, you're just jumping from the different
It's not like
supernet
search space where you could just go up and down.
Exactly. So this means that you have to jump into the different configurations of the data, and then there you optimize with respect to the supernet.
Yeah. But it is interesting and definitely future work. Like I already hinted a little bit that like I've also been experimenting now with trying to use some more gradient search spaces like darts and taking that and applying that.
The point here, but I mean, if you explore, I don't know, different resolution, different sizes, the problem becomes so this means that you will very quickly increase the number of different new supernets, and the training of each supernet is typically demanding in terms of data, time, and so on. Okay, sorry.
I don't have, no.
I'm also done. I asked my question. Okay. So, any more questions from the committee?
Yes, I do have one.
Last moment, huh?
If you would change something about your PhD, what do you
Okay.
No, that's always the right answer. Did you something different way since now you're at the end, the very end?
It's really easy to stand here and be like, this direction was a mistake to go to. I should have started like working on these things earlier. I mean that this data where NAS paper has like sort of been developed through a couple of iterations. First using a very, very simple search space that didn't even use supernets, and as you say, that quickly gets too slow for any like major applications. So perhaps if I could go back right now, I'd probably skip right over this step and like work with some advanced methods like this, or even the gradient descent method from the beginning. But I guess I went with what I thought. At the beginning, I thought that maybe this is enough and there's no need to overdo it in the beginning, which I also really don't think is a stupid approach to take to see if the simplest solution works first. And then it didn't once we scaled up to large scale data sets. Yeah.
And from the non-technical perspective, would you change something in your path, your journey of this PhD? I'm used to take this question.
Yeah, that's fair. I guess I should have expected them. Yeah. Maybe just in the beginning being more confident with settling on a topic and getting started on that. I think I felt that my PhD topic was quite open in the beginning, and that made it like, that means that you can do whatever. This is sort of like a blessing, but it's also a curse because you can do whatever. And I did spend a long time trying to like figure out where do I think I can make the most impact in these 3 years, and maybe longer than I should have, and I should just have gotten started early on something. But yeah, I did also thankfully get started, and this is also what I was thanking Jan for. He was pushing me a bit for that.
Thanks. Okay, thank you to the committee for a thorough technical discussion, scientific discussion. So next, the supervisors point test. Do you have any?
I will not ask any
question or comment that you want to?
Have 2 minutes. Or what?
6.
6, okay.
It was a very interesting discussion. It was a very nice presentation.
Thank you.
And Jan?
No, nothing special. I was going
enjoyed both the presentation, also the lengthy discussions and the interesting, but quite a bit around the topic.
Good. Then we actually have one question next to Auditoria. One. You'll save it for when you meet at the office next week. Okay, good. But then if there's no one else who wishes to pose a question, then this concludes the PhD defense. What will happen now is that the assessment committee, they will go and prepare a recommendation. It says as quickly as possible. Following that, the PhD committee will then process this recommendation, and finally that will then go to DTU's academic council for awarding the degree. And this concludes the defense proceedings. I don't know if you want to say something about if you have something planned.
Yeah, there's going to be a reception in building 324. That's this big glass building that is to the left when you just get out the door. First, I believe DTU has prepared something to drink, some snacks and so on. Later on, if you want, there's going to be some food that we get delivered. Yeah, you're welcome to stay. All of you, I've ordered some extra food for whoever else might be wanting to stick around. Yeah, and then, of course, just thank you very much for coming and enjoying this with me. Hope you're able to follow something.
And yeah, one small practical remark for the reception is that at this hour, DTU stores are locked, so make sure to follow along with someone, or no, sorry, in half an hour, they will lock. So if you exit during the reception, make sure to allow yourself to someone who can let you back in.
Don't they lock at 3 on Friday? 4? I don't know. I'm not sure it's 5 on Fridays.
Roughly.